Okay. Can you hear me?
Yes. Are you using the microphone of the surface?
Yes.
Okay, good.
Okay. Sorry for the delay. So, before starting the lecture of today, I would like to say that I added some slides on the shoulder singularity. There is also a video shows what happens. You can click on the link whenever there is a shoulder singularity. And we can discriminate the boundary singularity from the shoulder singularity by the fact that in both cases, there is a loss of influence of the joint motion on the end effector motion. But in the boundary case, we always have a solution for inverse kinematics. And in general, we can have a row of zeros in the Jacobian, or we can have two dependent rows. So we lose mobility in the direction represented by the range space sorry, by the null space of J pseudo inverse. But in the case of a shoulder singularity instead, we have that all the lines is above the shoulder axis are points of singularities. And in that case, we have a columns of zeros corresponding to the joint that lost the influence on the end effector. So there is just one or more joints dependent on how many columns of zeros we do have in the Jacobian at the singularity. And this means that whatever you put in that joint, it doesn't affect the end effector. And in inverse kinematics, you have infinite solutions for that joint. So this is just to conclude what was not really clear in the last lecture, in my opinion. And now we can start the chapter of the dynamics related to the Lagrangian approach. And so we will see two approaches in this course. One is the Lagrangian approach, and the other one is the Newton-Euler approach. And both of them have the purpose to derive the dynamic model of the robot. And the dynamic model of the robot is the one that provides a description of the relationship between the sources of emotions, which are the forces and moment, either internal or external, and the motion itself, the resulting motion caused by these forces. We can consider an application of these forces all along the structure, could be any point. For example, these forces could be the joint torques themselves, or, for example, external force coming from the environment. And these forces applied at different points needs to be transformed into the equivalent ones that we call generalized forces, that are the ones that will actually make the work on the generalized coordinates Q that we defined for the kinematics of the robot. The dynamic model will relate these generalized forces that we call U vector, that according to the nature of the robot could be, if nature of the joints could be either forces or torques in case we are talking about prismatic or rotational joints. And the dynamic model will allow us to compute the sequence of configuration that the robot will achieve as a consequence of applying these forces in a certain interval of time, for example. So we can derive the motion starting from the forces. This dynamic model is a set of second-order differential equations, because we are talking about rigid bodies, and rigid bodies are treated like masses. So force equal to mass times acceleration, and acceleration is it's a second order derivative of the position. And the number of equation of second order differential equation that we have is equal to what? To the number of degrees of freedom, or number of joints, or number of generalized coordinates with which we parameterize our joint space. Now, since this relationship of the dynamic model is bidirectional, we can talk about direct dynamics or inverse dynamics. And this has nothing to do with the inverse kinematics, where we were relating an effector and joint space, but it depends really on the kind of input that we have to the model. And for direct dynamics, the input is forces. For inverse dynamics, is motion or accelerations. So we start with direct dynamics, and if we select a force pattern, so a certain values for the joints in a time interval between 0 and t at certain time, this pattern of forces could be either sinusoidal, constant, we don't care. And we compute the motion given, so together with the pattern, we need to provide also the initial state that contains not only the position, but also the velocity, because we are talking about second order systems. And we saw that the state space equation has not only the position, but also the velocity. And solving the differential equation of the model, integrating that, we can get the motion of the joints along this time interval. So if I pay attention that if you apply a force in one joint at the instant 0, but you have, for example, a velocity that is in the other direction at the instant 0, so initial velocity that is non-zero, this means that the initial position will be could be in the opposite direction, actually. So the initial state really matters on determining the motion. And if we don't have a robot, for example, we can use this dynamic model to select, for example, the dynamic quantities like the masses of the links and inertia, because, for example, we want to predict what will be the acceleration over time given by the maximum torque provided by our motor. So we see what is the maximum acceleration, and we can tune the size of the links according to their weight and their inertia, and we can play around with simulation. And the simulation, it's always by performing a numerical integration. Why? Because we will get the model symbolically with the Lagrangian approach. We will see that with the Newton-Euler approach, the model will be only numerical. This symbolic equation could be converted inserting the values of the parameters, namely the masses, the link lengths, and the kinematic parameters in the center of mass and the inertias. They can be converted into numerical differential equations. But these numerical differential equations cannot be solved in closed form and needs to be integrated numerically, either resorting to, for example, a Runge-Kutta or Euler integration method. An important point is that we need to set the simulation step smaller than the sampling interval. So remember that the sampling interval is the interval to which we update the commands at actuators, and we read the sensors in the real system. But the simulation integration step should be smaller than TC because it represents the update of the states that are integrated in the equations, in the differential equations. So if we keep update the states only whenever, even if u is constant, because our actuator is keeping in a sampling time TC the actuation command constant, the state could evolve in time, and this is necessary to achieve an accurate simulation. Even though what we are really doing in the real robot will be to provide, we cannot go too much high with the TC, with the sampling time, because we have limited resources, computational resources on the robot, so we cannot compute too fast the actuation. But in the simulation, we can go with more accuracy. Actually, we should go with more accuracy to have a more realistic behavior, because the real robot will not move in step TC, but will continuously evolve. Okay. Now the direct dynamics, so the usage of a model in this way to predict the robot behavior, could be done for designing the controller. So I use the simulator and I design a controller and I close the loop and I see how it behaves. So exactly what we did for the lab with the electrical motor, we designed the controller and tune the parameter of the controller, seeing the effect on the robot that is simulated by the simulator. Or, as we said, it could be used for mechanical design. For example, you can check during with a certain controller, what are the efforts on the structure. You remember that we can compute them. We will see them in Newton-Euler. We can compute them. What are the torques involved if you want to size the actuators, because you want to define the motion first, and you want to work out what are the torques to select the actuator. So your committer requests some specification. It says the robot I want you to design needs to be able to do this motion going from here to there in a certain time. So it needs to have a certain acceleration, and then has this structure. And given this, you can check what are the necessary torques, and then select the actuators accordingly to the requested effort. While in terms of the inverse dynamics, we do the opposite. We have as input the desired motion for the robot in an interval between 0 and t, for example. And remember that this trajectory should be defined up to the acceleration level, because our differential equation is second order. And you, given this desired motion, once you have the model, you can ask yourself what are the torques, or the generalized forces in general, that are needed to achieve the motion, at least in nominal conditions. So with perfect, everything perfect. And these are the pattern of torques that are related to this motion that is defined at a position, a velocity, and acceleration level. And these are the torques that are needed to realize the motion. And this set of torques is unique in case the dimension of the joint state is equal to the dimension of these generalized forces, of this actuation state, we say but it's not unique in case of underactuation. We will briefly define next week, I think, what underactuation is. And underactuation is whenever we have a bigger number of degrees of freedom than the number of degrees of freedom that are actuated. So there are some degrees of freedom that are not actuated. Think about, for example, a legged robot standing on his legs, and his base, so his trunk, is a 6 degrees of freedom, represents 6 degrees of freedom that are underactuated. So it can only control the torques on the joint of the legs. And these are the degrees of freedom that are actuated. But we won't cover this in this course because this is a too advanced concept. And actually underactuation is kind of the opposite than redundancy. We can apply, you do inverse dynamics in two ways. We can apply, for example, a set of torques, check what is the resulting motion and see the difference between the resulting motion and the desired motion, and do iterative learning without any prior knowledge of the robot to learn this model. So this is one possible way of doing that. Otherwise, if you have a model, you can do the analytic computation of the torque that you need to get the motion, and at every time instant. And this computation, of course, should be efficient. And we will see that Newton-Euler algorithms are better better algorithm to do so. There is no integration in this case because we are talking about an algebraic evaluation of the torques given the states, desired states. And inverse dynamics is used for model-based control whenever you want to have a controller that has a knowledge of the model of the robot. So rather than just relying on the feedback to drive to track the desired trajectory, is already providing this necessary torque to realize the motion. So it's releasing the controller, the feedback part of the controller, from the effort to reduce the error, the tracking error. And this allows you to have higher performances. Or again, as actuator sizing, we said before, you can check the torque to achieve a certain motion and size the actuators. Okay. Then, so of these two approaches, one is the Lagrangian approach, is called Euler-Lagrange, and the other one is Newton-Euler. So Euler did a big job in that years, helped in both. He was a great mathematician and helped in both approaches. And the second one, the first one is the Euler-Lagrange is energy-based. And the two energies that are relevant for this macroscopic world are the kinetic and potential energy. And both methods, I need to say, they give the same dynamic model as output, even though the form of this model and the use of this model are different. The energy-based model from the Lagrange's approach are written in symbolic form, while the other one are in numerical. While the other one, they need some iteration and are numerical. You can study the properties of dynamical system with the Euler-Lagrange model, because you can directly manipulate the masses and central masses and do some conclusions with them. And you can analyze the control system, for example, study the global stability of a control system, doing Lyapunov analysis. We said that they are a symbolic closed form. The drawback of this, the main drawback of this approach is that these symbolic equations, they explode for many degrees of freedom. So it's really limited to a few degrees of freedom. And whenever you have more than 3, I would say, or 4 maximum, you should use the Newton-Euler approach. Actually, what we will use in the lab, in the last lab of this course, will be based on a Newton-Euler, recursive Newton-Euler approach. Okay. Newton-Euler it's just a generalization to the multi-body system, to multi-body system of the Newton and Euler equation, that is a balance of forces and torques for moments for a rigid body. So we do this for a serial chain of rigid bodies, and it's an efficient recursive implementation with iterations. And the recursion, it's starting from link 0 to link n, computing kinematic quantities like accelerations, and then with the back pass phase, reverse the recursion for the last link to the link 0 to compute the associated generalized forces. It's the best way to implement inverse dynamics algorithm in real time. Its complexity, it's linear to the number of degrees of freedom, and this is very, very good in terms of efficiency. Actually, is the best one, I would say. You can find and as I said, the dynamic equation are in numeric form. Okay. Now, let's do a quick review of how we compute kinetic energy. Consider a point mass, for example. Do you know what is the kinetic energy expression for a point mass? That it's described with a position P in a frame and a velocity V. Where V is a vector. What? Velocity squared, V is a vector, a 3D vector. So norm of. Okay, very good. That you can write this way, right? With the dot product, scalar product form. Okay, very good. And for a system of point masses, what do we do?
The sum of the kinetic energy of every masses.
Of every masses, okay. Yes. Okay, so the system, the whole system is the sum of the kinetic energies of the single point masses. But our assumption is that our robot is done of rigid body. We don't consider any flexibility. And in case of rigid bodies, what do we have? You have a linear velocity. Okay, but what else? What?
The mass is the overall mass of the body.
The overall mass?
Of the total mass of the body.
Yeah, but what a rigid body can do? Can only translate or can do something else?
We have a rotation.
Can rotate, okay. So linear velocity and angular velocity. And it's convenient to describe the rigid body motion using the velocity, linear velocity of one point specific, that is the center of mass. while the angular velocity, we say is the same is for all the points of the body. We define, we select a frame to do this derivation, F1, that is attached to the body and is centered at the center of mass, okay? And if we want to derive the quantities relevant for a rigid body, what do we have? So to compute the kinetic energy, we said that we had a mass, so we need to compute the mass for a rigid body. But this rigid body can have different densities. In some point could be more dense, in other points could be less dense, no? Density is not uniform. So what is the way to compute the, whenever you don't have a uniform density, right? We compute the integral volume of the small masses, small cubes. We discretize the rigid body with very many tiny cubes, and we sum them up, and the mass of each one will be the density in that point times the volume of that point. Density times volume equal to mass, no? And we do this, so this for all the volume. And this is called, we call it mass or zero moment of mass. We will see later on why. Then the second quantity we need, we said we have the velocity of the center of mass, so we need the position of the center of mass to define it. And how to compute the position of the center of mass for a rigid body? First is a 3D vector, right? Which is defined with respect to some frame. So it's a position vector with respect, needs a frame to definition. And we said we are using, let's say we use frame 0. And the definition of the center of mass is 1 over total mass of the body divided by P, where P is the position of the tiny cube, elementary volume we are considering discretizing the rigid body, P times dm. Okay, so it's like for each small volume we compute the mass, and we multiply for the position of that volume, and then we sum up, and finally we divide we integrate for all the masses. So we sum up, we integrate for all the tiny volumes, and finally we divide for the total mass of the rigid body, and this is called first moment of mass. You see here you have like a moment, right, passing from here to here. The COM position, it's like the position with respect to all the point kind of balance, right? So it's the position wherever we can concentrate, ideally as a point mass, all the rigid body. And where do we get the center of mass position? Usually we get this from the CAD model, we extract it from the CAD model, and usually this COM position is given in the link frame or in the COM frame. So it could be either in both. We see that later. So to compute again the position of the center of mass in an inertial frame, we need to use the homogeneous transforms that we see in the kinematics lectures. Now let's consider, for example, the case of two masses and define their position with respect to frame 0 in red on the left, And the total mass of a system of masses is m1 plus m2. And we want to compute the center of mass in this simple case. So we take the previous equation, we transform the integral as a summation, and we do this. So m1 times p1, which is the position of the first mass, plus m2 times p2, position of the second mass, and the pc is the position of the center of mass. Now, if we introduce, as we said, a COM frame, which is this one in blue, then we can define the position of the masses with respect to this frame, right? PC1 and PC2. So we do the same computation, and PC will be M1. We replace P1, which is PC plus PC1, and P2, which is PC plus PC2. Okay, then I can collect PC in both cases. And remain with M1 PC1 plus M2 PC2. We know that M equal to M plus 1, so this is M. These two can be simplified, and therefore this is equal M1 PC1 plus M2 PC2 is equal to 0. So we get this property, this nice property, if we select a frame at the center of mass. And this is true for any number of masses with positions defined with respect to the COM frame. Okay? Now, for a rigid body, what do we have? We have the previous form to compute. And we have the PC is 1 over m integral of position dm, and we say that if you select the frame on PC, this integral goes to 0. Okay, it's just a generalization to infinite number of infinitesimal volumes of what we just said. Now we want to compute the kinetic energy for the rigid body. And we will see that we will use this property to obtain a nice result. So we need to compute the kinetic energy of the infinitesimal volume filling the volume of the rigid body. So in this case, we have dm, and for each dm, we have its velocity that will depend on the position of the Lidl mass dm. Okay. Remember that we can express the velocity of a point in a rigid body using the fundamental kinematic relation for rigid bodies. We can express the velocity of a point of a rigid body to the velocity of another point, for example, the center of mass, plus the vector product of the angular velocity of the body times the distance of this point from the center of mass. So we can write this way: V is equal to Vc plus omega cross P, where it is a position of the m with respect to COM. And this, you can write it here. We can write omega cross already as a skew symmetric matrix. We have a transpose here, because we have a transpose here, and we okay. Then we have a term. We can split this product with all these terms, and we have one term like this, right? Which is the product of these two, plus we have a term like this that is double, so is the product of this times this plus the product of this times this, and since are scalar we can transpose and sum them up together, so the 1/2 goes away, and then finally we have the product of these two. So we have P transpose omega, because we transpose these two, and this is a transpose times these two. Now, if we look at this integral, we see that the center of mass does not depend on the position, so we can take out from the integral, and in this one, whatever doesn't depend on the integration position is the C, and also the omega. Well, P of course depends on the position. Therefore, we remain, for example, in this case, with 1/2 Vc integral dm, which is the total mass. Okay. While here we remain with Vc transpose omega cross integral of V P dm, which is equal to 0. Therefore, all this term is equal to 0. Okay. Now let's rewrite this last term. Let's go back putting everything together. So we have a linear translational part of the kinetic energy that depends only on the center of mass, and in essence, and in fact, is equal to the kinetic energy of a point mass m located at the center of mass. But this is not the whole story, because we have also a distribution of mass, and we have a rotational part, and this rotational part is affected by the distribution of mass. So we rewrite this here. And we keep working on this term, and we can notice that this is omega cross P all transposed, and this could be written as minus P cross omega, again transpose, and this could be written as minus omega transpose P transpose. Okay, while this one could be written as just swapping the two elements and putting a minus. Remember the property of cross product. So we have something that you can, is kind of symmetric, right? Is we have omega transpose, the minus goes away because we put one after each other, and we have P, symmetric matrix, transpose times P, symmetric omega. We see that omega doesn't depend on the integram position. We can take it out, is equal for all the points of the rigid body, and we remain with this expression, which becomes less ugly. I put some space here. That okay, looks like this. What is this, in your opinion?
Be the tensor of inertia.
Is the tensor of inertia computed about the center of mass, with respect to the center of mass. So this is, we call it ICOM. Remember, it's different, is the generalization to the space, 3D space, of what we saw for the single axis case, whatever we were calling it J, J1, J2, JM, JL, you remember? So this is the same thing, but in the 3D space. So the tensor of inertia represents the inertia to the rotation in the space. So if we define an omega and we have a torque, and we want to see, given a torque, what will be the angular acceleration around that axis, we can, around all the axes, we can see with the tensor of inertia that is defining the inertia around the free axis. What is the inertia to the rotation? And so ICOM is a tensor of inertia with respect to the center of mass. And then we can define this, express, so the frame where we compute the tensor of inertia is as the origin of the center of mass. Then the axis can be aligned either with the inertial frame 0 or with the link frame. We don't care, but so we care, but is not relevant for this derivation. Now we can define the following result, that is called Koenig theorem. Koenig theorem, where we have says that the kinetic energy of a system of a rigid body, for example, it's the sum of the kinetic energy associated to the movement of a center of mass and also rotational component that consider the inertia about the center of mass. So the second one is the rotational contribution, because only omega appears in a quadratic form to the kinetic energy of the body that takes into account the fact that we have a inertia distribution. So we don't have a concentrated point mass, but we have a body that is extended. Okay. If we would have only a point mass, we will end up only with this term. So this is a very nice. It's called second, because there is a first one, Koenig theorem, and this is translational part. Which is kinetic energy of point mass of the mass of a rigid body located at COM, while this one is rotational kinetic energy of a whole body and takes into account the inertial distribution through the inertia tensor, which is what? A 3x3 matrix that has this expression. And this is called the second moment of mass, because you see you have two elements depending on the position. And a moment is always a quantity, position times quantity. Sorry, it was already written. I didn't remember. So tells of inertia tells us how easily the body is able to rotate around some axis passing through the center of mass. And how we compute that? The expression is quite involved. We should do the integral for all the directions. Is quite involved. The property we can see here is that the tensor of inertia is symmetric, and so in general we don't do this unless we have very symmetric bodies that we will show there are some easy ways to compute this, to do these integrals. Otherwise, we use CAD data, and this is an example of tensor of inertia for the hip assembly link of our IQ robot. So the link that is moved by this joint, in essence. And you see here from the CAD, you get out the volume, you get out mass. This is almost 3 kilograms. You get the center of gravity with respect to the link frame. You can get the inertia tensor with respect to the link frame, or the inertia tensor again with respect to the center of gravity. So we get these numbers out. You see, because it's symmetric, we get only these two of diagonal terms will be all equal, and we get the inertia on the principal axis. And in case of homogeneous density with some geometric axis of symmetry, we can compute them with closed form formulas. In this case, for example, if you have a circle like this. We define the axis this way, and this is the moment of inertia about that axis. So this is just moment of inertia. So we call with J. Then we will see how to get the tensor of inertia out of them. So the moment of inertia in this case, for example, is just 1/2 mr², where we have a bar, okay? And again, the axis of symmetry we rotate about is this one. If the axis of symmetry we rotate about is this one, then you say you have a different expression. So we see that this time the radius doesn't account in the inertial computation. It accounts only the length of the bar. And in case of a parallelepipedum like this one, we get different moment of inertia about the free axis. So if we consider this axis, we consider we'll see that depends on the C length and on the B length, so on the cross-sectional area. And if we take the green axis, which is this one, we see that depends on A and on C. And if we take the blue axis, sorry, the black axis, which is this one, we depends on A and B. The axis could be passing through, for example, the edge of the body. This is a moment of inertia of a bar rotating around an axis about this edge. And in case of a point mass, if it is rotating about an axis, we compute the moment of inertia as mr², where r is the distance, minimum distance, with respect to the axis. That's why the inertia it's usually higher if the mass is distributed far away from the axis of rotation. So do you think, for example, if the mass is the same and you have a disk rotating about the x-axis, or something like this, an annulus, so a hollow disk, where is the higher inertia, moment of inertia here? Which of the two has the biggest J? The second one, because we distribute the same mass more far away from the axis. So in this case, for example, of a parallelepipedon, we can consider because we have this symmetry, we have a diagonal matrix, and we can provide fill in the matrix, the diagonal term of the matrix with the moment of inertia about the free axis. Okay, so it's quite easy. Whenever we have a link with a different structure, with different non-symmetric structure, we always have non-zero element on the diagonal. Okay, and we have also non-zero elements if the axis we are computing the tensor of inertia are not aligned with the axis of symmetry of our body. So if we have something like this, not aligned. Now, let's assume that we want to compute the tensor of inertia. So first, let's start about a simple case, the moment of inertia. So we have the moment of inertia about this axis, and we want to compute it around another axis. So the same example of before, that you got the bar rotating around an axis in the middle and one on the edge. And in this case, we have the parallel axis theorem that relates the moment of inertia around the z-axis to the one around the z prime axis to the one around the z-axis. And you see that you, in essence, have a bigger moment of inertia if the axis is not passing through the COM, but is shifted away. And the contribution is exactly the mr². So to compute the rotation, the moment of inertia about another axis, we consider the inertia about the COM, plus we consider the rigid body as a point mass, and we compute the contribution mr², because we saw that point mass contributes with respect to an axis in this way, as a moment of inertia of this shape. The extension to the 3D case. So a generalization to the 3D case is the Huygens-Steiner theorem, and in this case, the two frames we compute the tensor of inertia of we have the tensor of inertia about one frame attached at the COM, and we want to compute the tensor of inertia of another frame which is parallel, okay, with respect to the COM frame. For example, the frame 0. And in this case, it's similar to that. You have a center of mass, center of inertia, tensor of inertia, plus a term that is this shape. We have where we have the norm of the position, the square norm of the position, and the identity matrix, and this outer product that we saw a while ago. And this properties is equivalent to this. Remember, we saw this. Okay. Now let's talk about the potential energy. We now able to ideally to compute the kinetic energy. What about the potential energy? And first, let's recall what are conservative forces. Do you remember what a conservative force is? So, in the case of conservative forces, you can the work made by a conservative force depend on an initial and final position, and not on the path that you follow to achieve that. This means that because otherwise the moment will be the integral of the force times the x, the displacement. In this case, we can define a potential energy. So this elementary work will be differential in potential energy, for which at each position we can define a potential energy that represents the work of this conservative force. And the conservative force we are interested to describe is the gravity. And in this case, in the case of a point mass, the potential energy has this expression. So we kind of project the position of the center of mass along the gravity. So we get the height, let's say, of center of mass, and the higher the height along the gravity direction, the higher the potential energy. Then, okay, yeah, there is a minus sign because the gravity is pointing downward, so we need to have a positive potential energy. We need to flip the sign. For a rigid body, instead, we need to integrate through the volume again the little infinitesimal volumes with their positions. And we saw that since gravity is constant, we can take it out and we get exactly the expression of the center of mass position times m, okay? Now that we define also the potential energy for a rigid body, we can see the Lagrangian method to compute the dynamic model with using the of the model of the robot using the Lagrange method. Our assumption is that the links are rigid bodies. There is no flexibility. We have a set of Q generalized coordinate living in a joint space of dimension n that describe the joint configuration, and we can define a new function that we call the Lagrangian. The Lagrangian, it's not the sum of the total energy, which is the sum of kinetic and potential energy, but is the difference of kinetic and potential energy. And this is was derived. Lagrange itself, the mathematician, derived some condition according to which all the physical systems during the motion minimize this function. And this is called the principle of least action. We see that both the kinetic energy and the potential energy, they depend on the configuration. We know the kinetic energy should be always non-negative and is zero whenever it's zero, the kinetic energy. When velocity is zero, otherwise is always positive. And the potential energy is due to the fact we are in the robot is immersed in a gravity field, and the far away you are from the center of the Earth, the higher the potential energy, and while if you are closer to the center of the Earth, the potential energy is reduced. Therefore, you have position dependencies from the configuration. But we see that also the kinetic energy is dependent on the configuration. Do you know why? No. Or yes, but let's think about we have the velocity per center of masses, and we can have the inertia, the tensor of inertia, that is configuration dependent. So if you are an arm extended, your inertia tensor will be will be such that, for example, inertia about this axis is higher in the first case and lower in the second case. So you have a different rotational kinetic energy. Okay, but then it will end up into a dependency on the Jacobian. We will see that. So during a motion, every mechanical system tries to minimize the Lagrangian, and to take into account non-conservative forces, for example, like external forces coming from the joints or dissipative forces like friction, we will use the principle of virtual works that we defined in the last lecture. And if I don't have any external force, still the dynamic model we will find will work, and the robot, just from the initial state it starts, will collapse under the action of the only force, that is the gravity, and is conservative. As I said, I need to take into account the action of this, in case of I have external forces, the action of these external forces on the generalized coordinates. So in case we have, for example, Cartesian forces, we need to compute the Jacobian of the point of application of that Cartesian force, and using the Jacobian transpose, we compute the relative correspondent torques, because the torques are the, in case of only a robot with only rotational joints, are the generalized coordinates, forces related to the generalized coordinates. Okay. Now we can sum, as we did for the system of particles, of point masses. We can sum up the contribution of potential and kinetic energy for all the links, and compute the Lagrangian. So the total T and the total U compute the Lagrangian, and the Lagrange equations are the equations that we use to derive the model. And we said that the principle is this action minimizes the Lagrangian, and the expression of the Lagrange equation that is called the Lagrange equation that minimizes the Lagrangian is this shape, and is the d over dt of the partial derivative of the Lagrangian with respect to q dot minus the partial derivative of the Lagrangian with respect to q. And this is done for each joint. So we have an equation like this. Okay, we use partial derivative. Why? Because we have two dependency on two coordinates. One is the on two variables. One is the position of the joint. One is the velocity of the joints. And these ones are UI, the non-conservative forces that are performing work on the generalized coordinate. And they usually are on the right-hand side of the dynamics equation. And the effect of these non-generalized forces is to either change the energy of the system, either increasing it. For example, in case of motor torques, we accelerate the joints, or because if the motor torque changes the acceleration, the velocity increases, and therefore the kinetic energy increases, and so also the Lagrangian increases. Or we can decrease the energy. For example, with friction, we dissipate the energy and we reduce the kinetic energy. So we said we sum the contribution for all the links, and for link I, we use index I, and we rewrote whatever we wrote before for the rigid body, considering the ith link of the robot, where we attach a frame FCI to the COM. And since the kinetic energy is a scalar, these two quantities can be expressed in different frames at our convenience. So we can usually we define the velocity of the center of mass in an inertial frame, in the base frame, but these two, like the tensor of inertia and the omega, they should be, of course, in the same frame, because we are doing a projection here, for example. And it's convenient in this case to have the the tensor of inertia of the center of mass expressed in the link frame, because it becomes constant. So if we consider, as said, the frame that has an origin attached to the center of mass, but is aligned with the base frame, so we express in what we say, we express in the base frame the tensor of inertia about the COM. We will have a time, if the robot moves, if the link moves, we will have a time dependency due to the rotation matrix. And therefore, the tensor of inertia will not be constant. While if we define in the COM frame, since the COM frame moves with the link, the tensor of inertia is constant. Okay. Now, we said that the Lagrangian is dependent on Q and Q dot, and we can see exactly what you were saying. Where is the dependency? And dependency, it's due to the fact that not only the inertia but also the velocity of the body is dependent on the motion of the preceding links. So let's consider, for example, a link I located in the middle of the kinematic chain. And the same thing that we did for the computation of the geometric Jacobian for the end effector, we can say that the velocity of this body, it will depend only on the motion of the joints preceding the link. And so, therefore, we can use partial Jacobian, J lin I and J yang I, that will have some columns up to the column I that will be non-zero, while the other ones that consider the contributions of the joint velocities that are beyond the link we are considering in the serial chain, they are zeros because they don't affect the velocity and the linear angular velocity we are trying to compute. And this helps us to compute the final expression for the kinetic energy. So if from kinetic energy we factor out from that expression, we replace VCI and omega CI with J lin Q dot and J yang Q dot, we see that we can factor out the Q dot from all the summed terms, and we end up with this expression that allows us to compute what we called the inertia matrix. So all this big expression, it's becoming the inertia matrix of the robot M that has a dependency on Q and Q dot. Sorry, only on Q. While the dependency on Q dot is out here of the kinetic energy. So the kinetic energy is a quadratic form. What we can underline is what we said before, that we can express ICOM in a frame that is again attached to the COM but aligned with the base frame. So we need a rotation matrix. Sorry, this is okay, to match things, and of course the omega will be again also expressed in the zero frame, and this tensor of inertia will be time varying because this rotation matrix depends on the orientation of the link. And this matrix M is n times n symmetric matrix. We call it joint space inertia matrix, and it, because belongs to a quadratic form that represents the kinetic energy, and this kinetic energy is always non-negative. It means that it's zero only whenever the velocity is zero. This, you remember, leads to the definition of a positive definite matrix So M is not only symmetric, but is also positive definite, and this means that it's always invertible. No matter value of Q, we compute M. This means one important fact that we are able to isolate acceleration, the computation of acceleration in our dynamic computations. We are always able to isolate them. This whole derivation has been done to just show you that we have an inertia matrix coming out from the kinetic energy, but we will compute the inertia matrix not using these Jacobians. This is quite complex, but in a direct way. And the notation that we use in this course with M is different from the one used in the book of Siciliano, where he called the inertia matrix B. But I think it's better to call it M because it gives you more insights on the fact that it's an inertia. And we said that the inertia matrix depends on Q, okay? Because we have the Jacobian that depends on Q. So what is missing is the potential energy for the whole robot. We usually define the potential energy in an inertial frame or in the base frame. We have open kinematic chain, so we sum up all the potential energy, and the potential energy of a link depends only on the joint variable of the link that are predecessors of that link. And we assume that we have only a contribution due to gravity. We don't have any flexibility, so we don't have springs. So the only potential energy is the gravitational one, not the elastic one. And in this case, the potential energy of link I, it's the mass of link I times G0 transpose PCI in frame 0, where PCI is the position of COM of link I expressed in frame 0. And this is a projection along gravity. Again, what is the dependency on Q in this case? To compute PCI, we need to we set the position of the central mass in the last link in the ith link frame. It's constant, but we need to concatenate to get in the inertial frame 0 all the homogeneous transform that depends on the joint variables up to that point. Then summing up all the contribution, an important point is note that we define the gravity vector, and this gravity vector will depend on will have different coordinates according to where we locate the base frame. So if we locate the base frame with the z-axis vertical, then the gravity vector will have for example, a coordinate 0, 0, minus 9.81. But we are flexible, and we can, with this expression, allow to locate, for example, the base frame in other directions. For example, we want to attach the robot to a wall. In that case, the base frame can be aligned with the wall and have for example, the z-axis pointing downward. And in that case, the gravity vector would be 9.8100. Or we can have the robot attached to the ceiling. Think about, we got a request a while ago to work with a robot for the CERN accelerator of Geneva. And in that case, you need manipulators, anthropomorphic manipulators that are coming from the ceiling to pick objects in the accelerator. In that case, you will have a different orientation. So to compute, we can compute now the Lagrangian expression and consider the non-conservative forces performing work on the Q variables. So in this case, for example, we have the tau, or the friction, the joint torques, the friction, viscous friction components that depends on the velocity of the joint. We can have, usually we define a diagonal matrix for the viscous friction coefficient for all the joints, and we can have a column friction we saw, and also the external force exerted by the environment. You remember that this is the plus sign because the torque is yeah, this is the correct expression to account for them. In static case, you would have the torque on the other side, and you will see minus J transpose Fx. Then we can apply now the Lagrange equation to compute the dynamic model. And these are n equations, but I will, so they are from the joints from 1 to n, we have n lines, n equations. But to do this derivation, we need a little bit of taking a break because it's quite involved. So I will do, it's quite late. Let's do 5-minute break and then we continue. We try to finish this part at least.
Michele, before they come back from the break,
Yes.
well, sorry, before you end the lecture, don't forget to ask who's from artificial intelligence.
Yes, yes.
After they're back from the break.
Okay. Let's continue. So we can do the derivation either in matrix in vector format or in scalar format, and I decided to do it in vector format, but you can find the derivation in scalar format, for example, in the slides of De Luca.
Michele, before you continue, don't forget to ask.
Yeah. I need to know, I was asked from the coordinator of your course, how many people are from the AIS curricula in this course, and how many of them are following in presence? So just one in presence, and online, Samuel Bartolin. Okay, Alessandro Pini, 3. Okay. Yeah, maybe we should ask because maybe somebody went out. Okay.
I usually attend in presence, but on Tuesday I have some problem to come there.
Okay. No. The problem is not to know. Yeah, it's just yeah, the amount of people in presence or not in presence to do some evaluation for our organization. Okay, but anyway, I will check next week at the beginning of the lecture. Maybe is better. So if we now write the Lagrangian that we computed, we have the potential energy here, and the equations we want to use to compute the model are the Lagrange equation, and I write them here just to remember. And to avoid to use tensors, which are 3D matrices that are whenever you differentiate a matrix for a vector, byte vector, then we want to use the dyadic expansion of the mass matrix, and therefore we can write, for example, the M matrix considering its columns in employing the dyadic expansion, which is rewriting the matrix where we sum the columns with some AI vector that is a row vector, which is done like this. Sorry, it's a 1 in the ith position and a 0 elsewhere. Okay. Okay. Then this is called dyadic expansion. Then if we compute the derivative of the Lagrangian with respect to q dot, is a partial derivative because you have q and q dot, we have this expression, and to have a column vector, we need to transpose. Okay, let's take the this is the expression, and we saw that this is equivalent to nq q dot, and if we differentiate with respect to time this thing we just computed, we get mq times the derivative of the second one plus m q dot times q dot. Okay, and to compute m q dot dot, we can employ the dyadic expansion we just defined. So we do the summation between 1 and n of the derivative of the columns of the inertial matrix times q dot, because if we want to differentiate the matrix with respect to time, we can do the chain rule. We differentiate with respect to q, and then we differentiate q with respect to time, remember. Then we have the AI transpose vector that is multiplied by q dot, and this is just extracting the qi dot ith element, which is a scalar, from the q dot vector. Okay, then we need to compute the partial derivative with respect to q, which will this time the dependency on q is only on the inertial matrix, so we keep q dot as is. We do the derivative of m, because m depends on q, we use the differential, not the partial derivative, and then we write like this, minus the potential energy does depend on q as well, and we also differentiate that one. And this one, again, we can use the dyadic expansion. Of derivative of the column. Sorry, there is a q missing here, and this is again qi dot minus du over dq. Okay, then in essence we got we need to compute also du over dq. We take the expression we saw before, which is the summation of overall the links of the potential energy of each link, which is PCI, depends on Q. Therefore, we differentiate only that one which is nothing else than what? The Jacobian, in this case the linear one, of what? The COM of link I. And this is what we call, so it's a gravity vector, G of Q. Now, if we put everything together, are you finished? If we put everything together, we find, so we need to take this expression, this expression, this expression, and this expression, right? So we have mq dot q dot dot, mq dot dot, sorry, plus the two dyadic expansion, that is dmi dq minus 1/2 dmi dq. So this can be simplified times what? Q dot I, which is a scalar we computed before, times we take out the Q dot from before, because we had a Q dot here and we had a Q dot here. Then we have the gravity n equal to U. This is the joint space inertia matrix. This is the, we call it S of Q and Q dot, because we have dependency of both on Q and Q dot. We call it Coriolis centrifugal matrix. Then we have the gravity vector. And the generalized forces. So an important property that this matrix has is that if you sum up 2 times this matrix with the derivative of the mass matrix, you get a matrix that is skew symmetric. So it's like, let's call it Q matrix, where Q is skew symmetric. So if you do like minus 2s, you have always 0 for every x. And this will be very useful property to derive derivation of global stability, demonstration proof of the global stability with Lyapunov, and to design controllers. But we will not use. And so this is the joint space dynamic model, the full thing. And alternatively, it's possible to have the scalar version of this, where we do the computation for each component of the mass matrix. And we can see, if we look at one line of the Lagrange equation for one joint, the kth joint, but we have n of them. So if we look at one line, we can discriminate that we have inertial terms, that is, This is the multi-body version of the Newton equation, where we have a force equal to mass times acceleration. So we have the acceleration of the joint, and these are multiplied by the rho of inertial matrix relative to that joint. Then we also have a centrifugal terms that are, for example, whenever we see that here we have quadratic terms in the velocity. And these quadratic terms are of two types. Whenever you have I equal to j, we have centrifugal terms. Whenever I is different than j, we have mixed terms that are Coriolis. So this represents Coriolis forces, all this vector, and also centrifugal forces. Finally, we also have the gravity vector, the gravity component that is a nonlinear dependency on Q, because it depends on cosine and sine that are trigonometric functions and are nonlinear. So if to do some analysis, if we consider, for example, the term of the inertial matrix, which is KK, so the one on the diagonal, we can say that this is the inertia seen at joint K when joint K accelerates, and will bring all the joints that are after this joint. So we'll feel the inertia of all the joints that are beyond that joint. While the element Kj from mass matrix will be the inertia seen at joint K when the joint J accelerates. And this underlines the presence of inertial coupling. So if I move it, think about I have a 2 degrees of freedom robot, and I'm moving the first degrees of freedom with my hand, and the other one will do like this. And this means that it accelerates in the other direction. And this is a fact that shows that there are inertial couplings. So the motion of one joint, it's influenced by the torque, for example, applied from another joint, on another joint axis. And the other element is the Coriolis term. So in this case, whenever I and j are equal, we have the centrifugal force felt at joint K whenever joint I is moving, or in the other case, the Coriolis force felt at joint K, because we are talking about joint K now. We take one line of the equation, sorry. Whenever the both joint I and joint J are moving, and we will see example of these forces in a later example. Finally, I would like to conclude the lecture of today talking about the linearity of the dynamic model in the dynamical parameter. What are the dynamical parameters? Are masses, central masses, and inertias. And in absence of external forces, so for example, forces at the end effector, and using only torque, we can rewrite the dynamic model this way, and you use torques here. Wherever we collect all the dependencies on the q dot and q dot the terms that are dependent on this, on a matrix that is called regression matrix, while in the vector P we have all the dynamic parameters, the masses, the central masses, and the inertial tensors. And this way, we remember we can do whatever is called model identification. Using this equation, we do some motions in the air with our robot. We measure the joint velocities, acceleration, and position. We build the regression matrix. We also measure the joint torques for every instance. We create a big regressor set of regressor matrix and a big set of torques vectors put in column, and we can do the least square pseudo inverse of the regressor matrix, and we can compute the parameters that will be the best fit of that explains relates the torques and the position joint position velocity and acceleration, the best fit that relates torques to the motion. So you can identify in essence the dynamic parameter of your robot, because the CAD data, the ones that are provided by the CAD data, are not precise. Of course, they are just a good approximation, but they are not perfect. So if you want a more accurate, you need to do an identification of this parameter. Okay. Next time we show two examples on how to compute the dynamic model using the Lagrangian approach, and we will move to the Newton-Euler approach and discuss a lot about this Coriolis effect and inertial couplings that we will use in our controllers to improve the tracking accuracy, compensating for this inertial coupling. Okay, if you have any question.
I have a question more about the course itself, about if we have some exam dates, or if we decided about the type of exam.
Yeah, we will take a decision soon. Octavio, I think the first trial is 7th of June, right?
Yes, the first exam is 7th of June.
Okay, yeah, so sorry about that. I thought that you could visualize from the date of the exam, but yeah, we will do an announcement with all the details, take us a final decision, because the doodle we did for now, it seems quite balanced between the three options. So we will soon let you notify about what will happen. We also I was also told that for now the exam will be online. So in essence, it will happen this way. You will connect to Moodle, and this will activate a lockdown browser feature that will prevent you to go to use the computer. And you, in case the exam is written, then you need to use your phone camera connected to Zoom to visualize yourself while doing the exam. And then when the time is over, you will have 50 minutes to use either an app or like Cam Scanner to digitalize the document you wrote and then send me by email. So in essence, this is the procedure. And together with the picture of all the documents, you need to take a picture of yourself with the first page of the document, just to ensure that nobody did it in your place, the exam. Yeah, fortunately, these are the guidelines. And so see you next week if you don't have any other question.